On to conservation of energy. You can use conservation of energy if there is no external force acting on the system. It's true for conservation of momentum also. If your system is closed, then there is no exchanging of energy with your environment. If you have height and velocity, instantly think conservation of energy. Total mechanical energy in the beginning equals total mechanical energy in the end. Add up your energies. Do you have gravitational potential energy? Do you have spring potential energy? Do you have kinetic energy in the beginning? If so, okay, in the end, what kind of energies do you have? Do you have gravitational potential energy? Do you have spring potential energy? Do you have kinetic energy? Maybe you have rolling without friction happening, so you have rotational kinetic energy and translational kinetic energy. Just add up all of your energies in the beginning and have it equal all of your energies in the end. You're going to use that same equation if you do have friction or some other force that's not conservative and it's removing energy from the system. So when you're adding up all of your energies, gravitational potential energy, you might not be able to see that. So let's say I have gravitational potential energy and translational kinetic energy and rotational kinetic energy, and I'm losing energy to friction. So I'll subtract out work. Remember that work equals your change in kinetic energy. So you can treat the work done as an energy and include it in your conservation of energy equation, whatever situation you have there. In that case, also remember that work equals F times displacement. So if it equals F times displacement, then we could easily turn this equation into UG plus KT plus KR. And we know that our frictional force equals mu times Fn. So we can subtract out mu times Fn times our displacement. X, D, Y, whatever it is you're using, equals whatever energies we have in the end. And that'll work for you. You can solve for it. Just remember, if you're on a ramp, Fn is not equal to mg. Fn equals to mg cosine theta. So this would be mu mg cosine theta if you are on a ramp. If you're in space and you need to find an orbital velocity, you would set your big G gravitational potential energy plus your kinetic energy in the beginning equal to your big G gravitational potential energy plus your K. Remember, gravitational potential energy, big G, equals negative Gm m over R. Not R squared, just over R. What do we got next? Momentum. All right, for momentum, gravity will act as a center of mass. Gravity will act at the center of mass. That makes more sense. So whenever you have a rigid body, shape is not changing, is what a rigid body is. That's where the force is coming from. Just like your frictional force is coming from the contact with the floor, or your normal force is coming with contact with the surface, your force of gravity, your weight force, mg, that comes from the center of mass. To find your center of mass on a given coordinate system, you're going to take the sum of your your distance from the origin times your mass, plus your distance times the origin times your mass, and then divide it by the sum of your masses. So this allows you to find the center of mass for multiple points. You can find the center of mass there to be right here. No force acting, center of mass does not move. If you need to find the velocity for a center of mass, you would use a similar equation. Velocity for center of mass, you're going to add up your velocity times your mass. So that means v1, m1, v2, m2, plus v3, m3, however many masses you have, and divide it by m1 plus m2 plus m3. For acceleration, you just change all of these to A's. That'll give you your acceleration for the center of mass. Elastic collisions. Elastic collisions happens when there is energy conserved and momentum is conserved. Whenever you see that word collide or crashes, any synonym with that, you need to use conservation of momentum. From there, you need to determine, is this collision elastic or inelastic? It's going to be perfectly elastic or perfectly inelastic. In perfectly elastic, total kinetic energy is conserved. And the equation looks like this. P1 plus P2 equals P1F plus P2F. So then it becomes M1 V1 naught plus M2 V2 naught. Chances are, if it's multiple choice, at least one of these is going to be 0. M2 VF V2F plus M3 V3F. Right, so you have 4 different terms there. If it's an inelastic or sticky collision, then we're combining the masses. In this situation, momentum is conserved because momentum is conserved in all collisions. Angular momentum is conserved in all collisions as long as there is no external force acting on the system. So momentum is always conserved, and kinetic energy is not conserved with this. Some of the energy is dissipated out in the form of heat and sound. So for the inelastic, perfectly inelastic collision, you're going to have M1 V1 naught plus M2 V2 naught equals M1 plus M2 times the final speed of both of those combined masses. For an explosion, it's this same equation but in reverse. So you're going to start with a combined mass, M1 plus M2, times your starting speed, and that'll separate into however many pieces it separates into. Usually not more than 3. Momentum is always conserved without an external force, just like angular momentum is always conserved without an external torque. Momentum is a vector, so momentum in the x and momentum in the y must be conserved. If you have an object going in this direction before the collision, let's say it collides with something at rest, that means we have momentum that is both to the right and down. So after the collision, we need to have momentum equal to that, to the right, and this would be going faster, down. And if you added all these up, if I knew how to draw, all of my momentum to the right would equal all of my momentum to the left. Of course, momentum equals mass times velocity. For calculus students, you'll see it as the momentum derivative, or the time derivative of momentum, dp dt. So f is the slope of a p versus t graph. So if you have a p versus t graph and you have a slope, that slope is f. You can also get that from the impulse momentum theorem. Impulse momentum theorem says f delta t equals the integral of f with respect to t, which equals delta p. So in f delta t graph, I would say they're probably not going to ask you for a change in momentum. Well, if they do ask you for a change in momentum, it's just the area under the curve because we're multiplying these two axes together. And whenever you multiply two axes, you're taking that area. If we were dividing two axes, like p over t, then we would get f. Impulse is the change in momentum under the area. You can also find the change in velocity here because your mass is going to stay the same. Remember, change in momentum really means mass stays the same, but your velocity is changing. The curve of force versus time graph. This means that you can find velocity from this graph. Good for me. Now the good stuff, the part that you're afraid of. Please don't be afraid of it at this point. It's just the same thing as the translational stuff. Rotational statics. Torque is needed to create rotation. Torque is needed to change rotation is a better way to word that. So torque is needed to change rotation. If you want to slow something down, you need to apply a torque. If you want to speed something up, you need to apply a torque, as long as it's rotating. tau, torque, equals F cross R. And we always need the perpendicular component of either one of these. They have to be perpendicular to each other. So we can use sine theta. That's that cross. That cross means sine theta. Vector dot product. R is the moment arm or the vector arm, and it's the perpendicular distance from your axis of rotation. So I've seen some pretty weird things. Distance from or between force and the axis of rotation. That's what R is. Equilibrium happens when the net force equals 0, right? Well, that also happens when your net torque equals 0. So if you have a bar and there's a mass being hung from it, maybe from either side, if it's got an axis of rotation here, and it's also got a center of mass right here, remember that your torques clockwise have to equal your torques counterclockwise. So add up all of your torques. You can also just think about this as the torques that make it go minus the torques holding it back. And the torques that make it go are your counterclockwise minus your clockwise, equals mass times acceleration, right? Because this I is the rotational form of mass. Alpha, or angular acceleration, is a rotational form of acceleration. So this is just Newton's second law. Same exact thing. Of course, if it's in equilibrium, then you would set that equal to 0 and not IA, which is what I meant to write, but then I erased it all. So, to figure out, okay, which of these, what lines are clockwise and what are counterclockwise, you can just draw these little dotted lines, and that'll tell you. This is going against the way of a clock. Oh, sorry. That is. This red line is going this direction against the clock because our axis, our pivot point is right here. So then this one is going to pivot around this way. This one is going to pivot around this way. You can just pretend like each one of these is not there to figure out what direction. So your clockwise torques are both of these added together, and your counterclockwise is this one. Torque equals Fr, so it would be Fr, whatever force times the distance, the separation distance. And remember, this is the distance between the force acting and the pivot point. Don't let that trip you up. Something popped into my head. I said I need to review that to myself, and then, I don't know, I forgot it. So, you know. Equilibrium happens when the net torque equals 0. When in equilibrium, clockwise torque equals counterclockwise torque. When an object is rolling without slipping. Please look for that phrase, rolling without slipping. If you're looking at a wheel or anything like that, that means you have friction, and that friction is causing the torque. It is static friction, so it is not dissipating the energy. Only kinetic friction dissipates your energy. So rolling without slipping means that you have friction applying a torque, again at the surface. That would cause rotation in this direction. That's going to roll without slipping. Also rolling without slipping, we're going to get there, or maybe we did get there, but that means we have translational and rotational kinetic energy. So 1/2 mv squared plus 1/2 I omega squared. If you don't have omega, if omega is not given to you, it could be 1/2 I. What is omega? Omega is V over R. So it would be V squared over R squared. Well, if you don't have I either, then we can just say 1/2 M times R squared. If it's a ring, moment of inertia for a ring is mr squared. If it's not a ring, then it'll be given to you. Times V squared over R squared, and then you see the R squareds go away, and it's 1/2 mv squared. Moment of inertia is resistance to rotate. I is the sum of mr squareds. It's also equal to k, your shape constant, times mr squared. That k should be given to you. don't forget the summation. So you may have more than one piece of an object that is rotating. If you have a bar set on a disk that's rotating, then the disk will have rotational inertia, and the bar will have rotational inertia. The total rotational inertia for this system is going to be IB plus ID. So you add up all of your rotational inertias for complex objects. Mass closer to the center decreases the moment of inertia, allowing for easier rotation. If it allows for easier rotation, K equals 1/2 I omega squared. So if we make this smaller, that means your omega has to get a lot bigger to maintain the same amount of kinetic energy. If I'm spinning and I've got my arms out and then I bring them in, I'm going to spin faster. I won't demonstrate that because I think we've done that enough. Whew. Derive means to show each step. Identify the type of problem. Write the equation from the equation sheet. Set it equal to the situation. So if it's talking about deriving your coefficient of friction, or deriving your kinetic energy, let's say, derive your kinetic energy, well, we know K equals 1/2 mv squared. Well, you're probably going to need to use conservation of energy. UG plus K, R plus KT in the beginning equals whatever in the end. That's setting it equal to the situation. It's just making it make sense to the situation. The kinetic energy equation is given to you, but that's just your starting point. At least be able to find the starting point, write that down, because whenever you see this derive word, there's a lot of partial points available, a lot of partial credit. Gather those points. That's what we're trying to do. We're not trying to answer every single thing absolutely correctly. We're just collecting points, collecting points. That's it. Solve the equation for the variable asked for. Write your final expression in the correct terms. I kind of glossed over the important stuff. Solve the equation for the variable asked for. So if the problem says in terms of mu, R, L, and constants as appropriate, those constants can be things like little g or big G, those kind of things that are always constant. Please make sure you are simplifying your answer to get these things. So if V needs to be in your answer, but you have omega in your answer, you're going to use that same omega equals V over R relationship. And then probably when you put that in, R does something. All right. If you're not in calculus, this does not apply to you yet. I don't think that you will ever have to do this, but it's here. I equals the integral of R squared with respect to mass. So dm is just a ratio of, let's say if we're looking at a bar, it's dm to the mass is dx to the length. And what we're doing is we're cutting out an infinitesimally small piece here, and we're relating its mass to its length. So solving for dm, we get m over L times dx. All of that came from here. M over L is constant, and we're taking this, substituting it in up here, and pulling out the m over L, which is constant, integrating r squared to dr. Then we're going to set our limits. Those limits could be 0 to L, and then we're going to integrate. Rewrite it in correct terms. If you're not familiar with that, it's okay. It's going to be 3-4 points on the entire exam. So don't stress about that. Continuing on with moment of inertia, if an axis of rotation is moved to a new location, you're going to take the original moment of inertia and add mass times the distance moved to get the new rotational inertia. So it's going to look like this. Your I for the I whatever, IF, sure, equals I of the center of mass plus mr. Parallel axis theorem. Rotational kinematics. Remember your bridge equations. Those bridge equations are taking your translational thing and putting it over a radius. So if we're looking for angular acceleration, we're going to take our translational acceleration, put it over a radius. If we want angular velocity, we're going to take regular velocity, put it over a radius. If we want angular displacement, we're going to take regular displacement and put it over radius. You must have constant angular acceleration to use your angular kinematic equations. Remember those angular kinematic equations? Vf equals v naught plus a alpha, nice try, times t. And the no time equation, omega f squared equals omega naught squared plus 2 alpha delta theta. They're on your equation sheet. You can always go to them as necessary, as long as you have constant acceleration. If you don't have constant acceleration, you cannot use kinematics at all. Also, you can do calculus with them. D theta dt gives us omega. D omega dt gives us alpha. Remember, these are differential equations because we have a little calculus term in them. Please get your please get the point on the FRQ that says write but do not solve a differential equation for the net force. You're probably going to do stuff that makes it go minus stuff that holds it back. Equals mass times acceleration. FF that's me writing without thinking. We'll say FT minus FF equals m dv dt. That's a differential equation now. Of course, it's not simplified enough. You would need to go further. You probably solved for Ft earlier, and you know that frictional force is mu times Fn. That's all frictional force is. Mu times Fn. If it's on a flat surface, it's mg. If it's not on a flat surface, it's cosine theta. I'm excited to see how well you do. Everybody watching this. At least the ones that I teach. Because I am a little famous around the world. Newton's second law is still a thing. Alpha equals net torque over I. So just like F equals ma, or better yet, A equals F net over m. That's the correct version of Newton's second law. Torque equals rotational form of mass times rotational form of acceleration. Force diagrams or rigid body diagrams show where forces are acting. This happens a lot with torque. I did one earlier where I showed the friction acting here. The center of mass is where weight comes from. And then the normal force is the point of contact. It'd be the same thing for a thing on a ramp. We would have weight always goes down, mg. Then we would have normal force coming from the contact surface and friction going up the ramp. Friction always going up that ramp. Work equals FD, right? Or the integral of FdR. So then torque would equal, work done for rotation would equal the integral of torque d theta. That's a thing. But Mr. Scapetus, you never mentioned it. Maybe I did, maybe I didn't. Doesn't matter, because you know that stuff on the board. I don't know if you can see it, but let's see. You know this stuff. So you can turn any translational thing into rotational. K equals 1/2 I omega squared. Rolling without slipping is special. If you're rolling without slipping, then some of your total kinetic energy is spent to rotate the object, so both energies are there. Rotational kinetic energy and translational kinetic energy. This will slow down the object. Friction is being applied to rotate an object, so torque equals Ff times R, because F equals F. So you can substitute F anywhere for anything. Well, I just spent 2 minutes talking to absolutely nobody because my microphone was off. But it's good because I was kind of rambling, so let's focus. Regular momentum, P equals mv. Angular momentum is L. Rotational version of I, rotational version of M, rotational version of V, right there. L equals I times omega. L and P, the weird letters for momentum. Angular momentum is always, 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 always conserved until it's not. And it's not conserved when there's an external torque acting on a system. Like, let's say a comet hitting the Earth would be an external torque knocking us out of our orbit and changing our total angular momentum. So angular momentum equals I times omega. It also equals mvr. This mvr here, this is more useful if you have the puck going this way and then it's going to hit the pole, right? So this puck has angular momentum mvr about this point. And the way you can think about that is if it were going, it would be rotating in a circle. Then once it exerts a torque at this point, it's going to rotate in this direction, and now this has angular momentum I times omega because it's now rotating. So if it's rotating, we use I times omega. If it's not rotating, mvr. Change in momentum equals impulse, F delta t. So our change in angular momentum equals tau delta t. Because they're the same exact thing. They behave the same exact way. The differential equation involving angular momentum is dl dt. So we could do F equals dp dt. Right? Because translational version, translation. They're the same exact things. Direction of angular momentum depends on the cross product. L equals P cross R. P is mv. That's this. So V and R, theta has to be perpendicular to each other. So momentum vector and the arm vector has to be perpendicular to each other. So it would really be L equals mvr sine theta. Just in case you have an angle between your velocity and your lever arm. Distance from axis of rotation. Sorry, getting tired. Two disks colliding means torques applied are internal. You have to ask yourself, is this collision elastic or inelastic? If they stick together, then it's inelastic. So you would just say, I don't know if you can read that, but it's good stuff. L naught equals LF. L1 naught plus L2 naught equals L1F plus L2F, which would be I times omega plus maybe mvr equals I times omega plus I times omega. If the objects stick together, or maybe you have two disks rotating, then it would be I times omega plus I times omega equals I times omega. F, 2, 1. You know how this stuff works. 2, not 1. Right? If they stick together, then it would be L1 naught plus L2 naught equals I1 plus I2 masses combined times omega F. One velocity if they stick together. So this is sticky. Oscillations. Simple harmonic motion is a special type of periodic motion. Simple harmonic motion happens when your force is directly proportional to the opposite of your displacement. Opposite direction. But as you if you have a spring, a mass on a spring, as that force, or excuse me, as that displacement is getting bigger, so as that spring compresses, then the spring force, so if X is happening to the left, then the force would be happening to the right. And the more you compress the spring to the left, the greater the force is to the right, because that force is a restoring force. It's trying to get it back to the equilibrium point. Of course, inertia is going to cause it to overshoot its equilibrium point, and then the whole situation is reversed, and the X will be extended to the right, and force will be directed back towards equilibrium. Also, this will result in a sinusoidal position versus time graph. Sinusoidal just means sine-like curve. Looks like that. X, maximum cosine of omega t plus phi the phase shift. The phase shift is just how much is it changed, how much is it shifted over. Remember that if you are dealing with a graph that starts from 0 and goes positive, this is sine. If you start with a graph that starts positive and goes towards 0, this is cosine. If you start with a graph that starts at 0 and goes negative, this is negative sine. And then finally, if you start a graph that starts negative and goes towards 0, this is negative cosine. Know the order of this: sine, cosine, negative cosine. That's as much of the pattern that you're going to need, because you can take the slope of one to go to the other. So if your position is given as a sine curve, starts at 0 and goes positive, then you know your velocity is going to be a cosine curve, starts positive and goes negative. Then that means your acceleration, the derivative or slope of that graph, is going to be a negative sine graph. Starts 0, goes negative. You can also remember the shortcut that if your position versus time graph looks like this, then your acceleration versus time graph is going to be a mirror image flipped over the x-axis. So if it starts out as cosine, it's going to end up being a negative cosine for your acceleration. If you have to differentiate this function, remember to use your chain rule. To use the chain rule, we're going to take the derivative inside here and then multiply it by the stuff outside, keeping what's inside the parentheses the same. When you see simple harmonic motion, think about a pendulum moving back and forth, because a pendulum moving back and forth is going to have its maximum potential energy right here and its maximum kinetic energy down here. And it's just going to continue to go back and forth. So if we plot the position versus time, it's just going to continue to go back and forth. This is its maximum displacement. Maximum displacement, minimum displacement, it would be here, or x equals 0 would happen at the equilibrium point. Maximum velocity happens at your equilibrium for pendulum, mass on a spring, any of that. Maximum gravitational potential energy, as I just showed you, happens at your amplitude. Amplitude is your maximum displacement. Newton's second law is a thing, so we can say the net force equals mass times acceleration. So you can say if the force, only force acting on a spring oscillating, let's say you have square and that, and it's going back and forth, the only force acting on it, if it's on a frictionless surface, could be the spring force. So the spring force is negative kx, Hooke's law, equals mass times acceleration. If you need a differential equation, there you go. It can also be the second derivative of x, so that way you have your x terms. It's a thing. Use it. Is that it? No, it is not. Period is the time it takes or the time it would take for one complete motion. The period mistake. Your angular frequency is 2 pi over omega. So if you have f, you can substitute 2 pi over omega. Your period is the inverse of your frequency, and your frequency is the inverse of its period. Spring potential energy is 1/2 kx squared. Energy is always, always, always conserved unless there's an external force or a non-conservative force acting to dissipate that energy. If there is an outside force, the period is the same. It's just a shorter distance in a longer amount of time. So your period is unaffected by dampened motion. Period for a spring, period for a pendulum. Know that mass affects your spring, the period of a spring, while mass and spring constant. While for a pendulum, only the length and the planet that you are on will affect the period of a pendulum. That's it! Okay, so good luck on your exam. Breathe, take your time. If you're spending too much time on one question, put a star next to it and come back. A lot of you have testing strategies where you will pick an answer and then move on. I like that because you don't leave it blank, so there's no chance of you turning in a sheet without an answer. Because if you're not taking a guess on a multiple choice question, you are only hurting yourself. Find the free points. Collect those free points. Make sure you're labeling your free body diagrams. Make sure you're drawing those arrows proportional in length. Their length should be proportional to their magnitude. Magnitude just means absolute value. There's so much stuff. You can do it. I believe in you. Good luck.